Thank you very much. Thank you everybody who is participating in this vacation time, in this seminar. Well, Josef already said one half of my talk that I was going to explain. I am theoretician, so even though I'm going to talk about experiments, so that's warning ahead, so that you cannot expect too much details from me. But on the occasion of the start of the run 3 of the LHC, it seemed to be appropriate or good time to review what the LHC is about and what is the run 3 about. So I prepared 3 talks, and the first one, as Josef said, was about the major 4 experiments and what is the update for round 3. In the second we were talking about physics, and today I would like to talk about something I call small experiments. And it is interesting. It was interesting for me to dive into this topic, because not too many people, not even too many experts working at LHC, are familiar with these small experiments that are running alongside of the major 4 experiments. And so this talk is sort of review and explanation what these experiments are, what they serve for, and what's the physics that is investigated there. Okay, so the must be shown picture of the LHC and Geneva region and Alps. So I don't have to perhaps say anything about this, you are familiar with this picture. Perhaps just to get to remind that the 4 major detectors, LHCb, ELIS, CMS and Atlas, are in these spots. And the whole LHC is not just a single accelerator, but it's a set of, or cascade of many accelerators, where protons eventually would achieve the expected energy. And for round 3, it's 13.6.
Yes.
Sorry. That's embarrassing, but I suddenly wasn't sure what's the energy for round 3. So it's 13.6 GeV. TeV, still not 14 TeV that was advertised in the beginning, but perhaps we will get there in the following years. For non-accelerated physicists, again, I just remind that this is a collider where proton beams are accelerated in opposite directions, and they collide in these 4 colliding interaction points. And at this point, these points are surrounded by these big major detectors. But besides that, there are these small or minor dedicated detectors. Why I say dedicated? Because CMS and Atlas detectors are so-called general purpose detectors. That means there's that they are prepared, there are huge machines prepared to detect and analyze all kinds of scenarios, all kinds of particles. ELIS is more dedicated. It's not so general. It's mostly for detection of coagulum plasma. And LHCb is also a little bit dedicated towards investigation of the physics related to B quarks. But still, these four detectors, I call them the major, because they are also big, very big, much bigger than the detectors we are going to talk about today. So those are those that are shown in blue color. I indicate their names and also the year where they started, where they begin their functioning. So taking it from the oldest one, there are two experiments called TOTEM and LHCF. Then after that, in 2011, there was third experiment called MOEDAL. These are also, of course, these are acronyms, and I will explain what these acronyms mean. In 2017, the milliQuem experiment started, and then most recently, or for this round 3, there are two new experiments, SND and Phaser. And in preparation, there is one more experiment, Mathusla, which is in the preparation stage. The prototype is built, but its full functionality is expected to occur in several years, where the LHC will be further upgraded to so-called high luminosity LHC. So these are experiments I'm going to talk about. So let's start chronologically. First two experiments, which are as old as the LHC itself, are the TOTEM and LHCF. The LHCF is located very close to the Atlas detector. TOTEM is located very close to CMS detector. And both these experiments are using or detecting particles that emerge at their respective interaction points. So let's start with LHCF. LHCF is basically stands for LHC forward. Why this name? I will show you in the next slide, but first, what's the physics that is investigated by this detector? It is dedicated to measurement of or simulation of cosmic ray cascade. Or it's the first interaction point where the proton from the cosmic ray hits nucleus or other hadron particle nuclei in our atmosphere. Because the physics theory behind this is QCD, non-perturbative QCD. We are not able to calculate too much about this interaction, and if we want to investigate and understand properly the whole cascade of the cosmic rays that are detected at the ground or at some height, we have to well understand the first collision that occurs. But we are not able to calculate it theoretically, so we at least can try to understand it from the experimental point of view and to set up some phenomenology that would properly describe this first interaction, and then based on this on the phenomenology of this first interaction, we can more precisely describe the following avalanche of particles. So the LHCF detector detects pions, their energy and the number of pions, the neutral pions that emerge either in the proton-proton collision or proton on lead collision that already has been looked at and measured, and the new collisions that are more or closer to the reality of the proton hitting our atoms in our atmosphere will be proton on oxygen collisions that will take place in this new round 3 of the LHC. So the experimental setup of this experiment is depicted in this picture. This is Atlas detector. This is interaction point where protons are colliding. Oops. These are two tubes that are bringing protons in and out. After the Atlas detector, they split into two tubes. And the LHCF detector, that is, as I said, that is supposed to detect neutral ions, is put in between these two tubes, proton tubes. What you can see on this picture is only one of two detectors, because there are two symmetrically on both sides of the Atlas detector in the distance of about 140 meters from the interaction point. And it is a very small detector indeed. You can see it here on this picture. Basically, this part is the detector itself, and this is some box with electronics. So you could put it on the table like this, and that's all what is there. So it's a huge contrast if you know how huge the Atlas detector is. Then this is really very tiny thing. But still, it serves or investigates very interesting physics, and it's sort of unique. It provides unique perspective or unique input into investigation of the cosmic ray interaction with the atmosphere. Okay. If we want to set up where those pions or where those collisions at the LHC would be placed within the energy spectrum of ultra-high energy cosmic rays. So this is a graph, this is plot of the flux of the cosmic rays versus the energy. This is flux multiplied by the third power of energy, so it's not decreasing as we perhaps are familiar with the graph where the spectrum is really steeply down. When we collide protons with at the LHC close to 14 TeV, then it is equivalent to the cosmic ray collision, cosmic rays of this energy. LHC in its previous runs was running at lower energies, so these arrows indicate roughly the positions from where the LHCF detector was probing this spectrum. Okay, another experiment on the opposite side of the LHC, which is close to CMS detector, is totem detector. Totem stands for total cross-section elastic scattering and diffraction dissociation measurements. You can see that the whole name provides, you can make up a lot of various names. There's a lot of letters.
A lot of options.
So you can finish, you can make up acronym as you wish. But they chose totem. And what is it for? Basically, it investigates proton-proton collisions at energies which are far from perturbative region. That means, again, it's experimental investigation of the collisions where we are not able to calculate theoretical predictions, or where our ability to calculate something is very limited. Therefore, we need input from experiment to improve our understanding of what's going on in proton-proton collisions in such regime. And this totem detector investigates on first total cross-section, elastic cross-section, and inelastic cross-section for proton-proton collision. There are some non-perturbative methods that are used to describe, and they were popular in the 60s, even before the QCD was formulated for description of strong interactions. And they are still, they predicted the existence of some pseudo-particles like pomerons and oderons, which are not real particles, but there are some, like in solid state physics, we have phonons and other stuff like that. And also in these strong interactions outside of perturbative region, there are some predictions of these pseudo-particles. And indeed, this experiment detected such pseudo-particle called oderon. These are quantum states of bound gluon colorless states, and oderon is mostly is dominated by 3 gluon colorless state. It was the discovery of this pseudo-particle was confirmed in December 2020. And besides this, this investigation also enables somehow to establish the cross-section these cross-sections independently of the luminosity. Because the traditional way to establish the cross-section is, okay, we know the luminosity of our beams that are colliding, we count how many events we found in the final state, and then simply dividing the number of events by luminosity, we end up with the cross-section. Of course, this calculation of, or this measurement of cross-section depends on how well we know the luminosity of our beams. And this experiment enables to determine luminosity, cross-section independently of the luminosity, and therefore it also can serve as the independent method of measurement luminosity of the LHC beams. Okay, these are photographs of how small, again, how small this device is. Much smaller than CMS detector. Again, we can put it on the table. And fine. Now the third detector is called I'm not sure how to pronounce it. how people who devised this how to pronounce it. But it stands for monopole and exotic particle detector at the LHC. So from there you can infer that the main purpose of this detector is to detect hypothetical magnetic monopoles. And it looks like this. It's not as small as previous two detectors. This is LHCb, and this part is this Moedal experiment. And theory, of course, the magnetic monopoles are around for some decades. The first who formulated hypothesis or showed that something like that could exist was Dirac in 1931, and then grand unified theories in 1970s put this idea on the whole new platform, much elaborated picture. But still there is a lot of maneuvering space, so expected mass of this hypothetical magnetic monopole ranges between 1 to 10 to the 14th TeV. So when we are so much uncertain about the mass of the particle we want to detect, it's quite difficult to set up the device that would serve for the whole range of the masses. But yet still they managed to build such detector. And basically it's based on the idea that magnetic monopoles or other very massive particles that are stable, it means that they do not decay inside the detector or even before they reach the detector, they would be highly ionizing. And that means that they can use traditional nuclear track detectors, which I understand that it's plastic pieces, plastic material, and these hypothetical highly ionizing particles would leave some scratches, destroy along the path, the plastic, and then by applying some acid you can enhance these marks in the material and then study how many such particles went through the plastic material. This plastic material is interlaced with aluminium bars which serve to slow magnetic monopoles, and in the case that the stable massive particles traveling through the detector would decay, but not very soon, so they leave some significant part of the track. Then this detector uses so-called Schwinger effect to detect such particles. That means this particle would have such strong electric field, they would be surrounded by such strong electric fields that they would spontaneously create electron-positron pairs, and by detecting these pairs we would deduce that such particle was there. So it's very interesting experiment, very interesting detector, but despite the fact that it's been around for a decade, no signals were observed yet, so no magnetic monopoles. And by the way, the dions are magnetic monopoles with electric, which have besides magnetic charge also electric charge. Okay, another detector close to CMS, which started at 2017, is milliQuem. It serves for searching for milli-charged particles. That means some theories, especially theories of the hidden sector of the Standard Model, predict the existence of particles which would have an electric charge of the size of a very small fraction of the electron charge. And the question, therefore, it's a good question to ask if we were able to detect such particles. And indeed, this detector is designed to do that. And the overall setup looks like this. This is interaction point for CMS. Protons are colliding, and then in this room, which is separated from the CMS detector by the wall of the width of 20 meters, there are detectors who are trying to detect charged particles. The point of this wall is that the ionization is proportional to the square of the charge of the particle. That means the standardly charged, that means it's the charge 1 electron or very close to it, they would be stopped by this wall, and only particles with very small fraction of electric charge be able to penetrate this wall, because they do not ionize this material as much, and they would not, therefore they would not lose too much energy. This experiment is predicted to have sensitivity 1/1000th of electron charge for the particles of the mass of 1 GeV, and 1/100th of the electron charge for the mass of particle of 10 GeV. Again, no such particles there or has been found yet. Another experiment called phaser, forward search experiment. It's close to the Atlas detector, but not as close as the previous detectors. This one is about half of a kilometer from the Atlas interaction point. You can see this is a picture that shows you tunnels. This is SPS tunnel, this is LHC tunnel, and there is some tunnel which is interconnecting these two tunnels. This is the Atlas detector, placed for the Atlas detector and interaction point, and the phaser detector is placed very close to this crossroad. And the point is that whatever is produced in these collisions, and it's produced in a very narrow beam of particles along the side of the colliding beams of protons, would be detected, would reach this phaser detector. So this is how this phaser detector looks like. First part is the wire which detects neutrinos. Then there is some decay volume for other type of particles than neutrinos, and the rest are detectors for detecting these particles, which would decay somewhere in this volume. Again, you can see that it's not a very large detector. This is the scale of 1 meter, and the whole thing serves to search for new light and weakly interacting particles, which besides neutrinos could be particles like dark photons, axion-like particles, sterile neutrinos. The fact that this detector is sensitive only to the light particles, that means with small mass, because it should be produced in rare decays of hadrons, which are created after the collision of protons. The positioning of this detector narrows the possible detected particles to forward direction, and also because these forward direction particles are directed forward when they are highly boosted, then this causes these particles to be only not to decay before reaching this detector. And as I said, this first part serves for detecting neutrinos, standard neutrinos, and this is a detector that would detect the most energetic neutrinos produced under controlled conditions, all 3 flavors of neutrinos, and about 10,000 neutrinos should be detected during the lifetime of this experiment. Okay, the counterpart of this phaser detector would be SMD detector. It's right symmetrically on the other side of the Atlas detector, and even in the same distance. Phaser was here, and SMD is on this side. These are 2 independent groups, 2 independent detectors. They have their own designs, so therefore it's opposite to the first, what was it, not totem, but LHCF. LHCF was one detector with 2 parts on both sides of atlas, but SND is independent detector from phasor. And it's scattering, SND stands for scattering and neutrino detector. Again, this is atlas detector and collision point, and SND is somewhere there. Primary goals are detection of neutrinos, which are created in proton-proton collisions. They would originate primarily from the decay of sharp quarks to strange quarks and W plus minus, which then further decays into neutrinos and leptons. And this experiment, by detecting these neutrinos, they are also able to study gluon parton distribution functions. That means how the momentum is distributed inside the proton among the gluons and quarks. Besides known neutrinos, this detector should be able to detect feebly interacting particles. Don't ask me what's the difference between feebly and weakly. Perhaps it's even weaker than weak. And the candidates for these particles are massive gravitons particles, which are possible candidates for dark matter particles, particles that are predicted by the hidden sector of the standard model. By this experiment, this experiment would contribute to the explanation or measurement of neutrino masses, because as you are probably aware, the current existing measurements, provides two possible solutions of the mass spectrum of the known neutrinos, and also this experiment can contribute to some other questions of the present particle physics. Okay, so these are experiments that has been or are running at the present. And there is one last experiment that is already in its preparation, but it will be fully functional in several years when the LHC is upgraded even further. The luminosity will be enlarged so that it will be called high luminosity LHC, and it is positioned at the CMS detector. And the role of this, or first the name ATCUSLA, comes from massive timing hodoscope for ultra-stable neutral particles. And the role of this detector, which is not as small as the previous ones, is to detect exotic neutral long-lived particles with a lifetime up to 1/10 or even 1 second. Such long-lived light particles would escape the CMS detection, and which is illustrated in this picture. This is CMS detector, and this would be this MATUSLA detector, which mostly it's a large room or large hall, which is 100 times 100 meter square, and it will enable to detect particles that will be decaying after traversing this distance. You can see the measurements. This is 60 meters. This is about almost 200 meters. This would be 100 meter. And it's about 20 meter. It's digged, partially digged into the ground, about 20 meters. And again, this positioning of this detector away from the CMS is basically due to need to wait to let this particle to decay, because when they are neutral, they are not leaving any traces, they are not detectable. So we have to wait until they turn into electrically charged particles, and then we can use standard means to detect their decay products and then deduce from that the existence of such particles. So, okay. So summary. So this is the list of small detectors at the LHC. I hope that there are some other hidden which I didn't find about. But I'm sure that people are thinking about and trying to use every opportunity to put something somewhere that could use this unique LHC collider to good use. And again, so in summary, we were talking about LHCF, which serves for simulation of the cosmic rays, about TOTEM, which measures non-perturbative region of the proton-proton collisions. MOEDAL serves to detect magnetic monopoles and other stable, very massive particles. MILIQUEN serves to detect particles which would have only a very small fraction of the electric charge of electron or positron. Phaser is a detector designed to measure very high energy neutrinos and to possibly detect other light and weakly interacting particles. SND is sort of doing the same thing as phaser, but it's independent experiment. That means it's designed independently, it's not a copy of phaser. There are used other methods how to detect these particles, which is always useful when you measure the same thing in two independent ways. And MATUSLA is this experiment preparation, which would detect exotic neutral long-lived particles. So that's all about small detectors at the LHC, and thank you for your attention.